All right, so last section here, nonparametric regression and causal inference. So remember, when we're doing regression for causal inference, the reason we do this is because we have this plugin estimator. We have this identification result that says if I'm looking for the average value of this potential outcome, I could get that under identification conditions as long as I have no unmeasured confounders. All I need is this conditional mean of y given x and a, and then what I need to do is just say, use this like a prediction model, and I say, put in here, what would happen to all of these people if I set a to be 1 and take the average prediction of that? So of course we don't have this true conditional mean, so we have to estimate it, and we don't have the population, so we have to estimate it using a sample. And the question is, how do we get this, how do we estimate this conditional mean function? And of course we use that using machine learning. We've done it with linear regression, we've done it with logistic regression, now we're going to do it with machine learning, but it's the same process. The only thing is that, and technically you should do this with linear regression too, but because of this overfitting problem, it's very important in machine learning because it's very easy to overfit. Because of this, you should always use what's called the cross-fit regression plugin. And it's a very similar idea to this kind of cross-validation idea. The point is that if you train a machine learning model with a particular person in the training set, and then you say, what's the prediction for that person? The machine learning model has already seen the outcome. So it could just kind of memorize the outcome and give you back the outcome. And you're going to have very good predictions, but it's not actually reflective of the test set performance. So what you want to do is for each person, you want each person to be kind of like in their own test set. So you want to train a model using everyone else, leaving that person out, and then get the prediction. And then start from scratch, train a model using everyone except for the second person, and then generate the prediction for the second person, and then go on and like that. And you can do this, you don't have to do it individual by individual, you can do it in folds. So you can do kind of like 5-fold cross-fitting. And this way everyone gets a prediction, but that prediction is generated from a model that never saw that person in the training set. If you don't do that, you're gonna get wonky stuff. So here's the algorithm for doing that kind of manually. So I put this in a function where I'm getting the kind of splits. So for each split, I can call training and testing to get the training and the test set. And here model is whatever random forest or whatever things that I've initialized. So here I take my model and I fit using the training split. And then for the testing data, I generate my predictions where I've mutated a to be 0, and then the predictions where I've mutated a to be 1. So these are my counterfactual predictions for the people in the test set. Now, how do I then generate predictions for everyone? I just loop, so that's mapdf, over the different splits. And that's going to give me predictions for everyone in the data. And something to note here is that here I just have model, right? So here I've said models, nearest neighbors, whatever. But if I were doing this in practice, I would not just specify, again, just this to be nearest neighbors. I would do a whole cross-validation thing inside of this to figure out whether neural network or random forest, what hyperparameters work best. And it looks like a lot of code. It's kind of a lot of complexity when you first see it. But after a while, this becomes very routine. And the key is that once you've done it once, you really don't have to think about it again. And it's all about just making sure that you're not double dipping on the data. So you're not making predictions for one person using a model that's already looked at that person, and that when you're picking what model to use in general, you're also not looking at the data that you use to train the model to evaluate that model. So all of this is kind of like nested cross-validation or nested data splitting to do model selection and then prediction out of sample prediction. Here I'm doing a simple case where I pre-specify I'm going to use this nearest neighbors regression method. So here's what that looks like. So here I've generated a data set where the empty dots, this is like the y0 that I'm not observing, and the filled dots are the y0 that I am observing. So I have like both potential outcomes here. And I'm showing you the regression fit from this machine learning method. And these are out of sample predictions. So for each filled in dot, I'm getting the prediction from a machine learning method that has been trained without that data point in the training data for it. So I'm getting the predictions for for everyone. And you can see that even in the region where there's not a lot of treated people, the machine learning model is doing a pretty good job at predicting what would happen for people if they had been treated. Similarly, for the untreated, right, over here, it's doing a pretty good job predicting for these people what would have happened if they had not been treated. Whereas if I'm using linear regression, these are the fits. And this is linear regression. It looks wobbly. And the reason, because there's actually like 5 different linear regression models here, because I'm doing the out of sample prediction. So these are the predictions kind of from each there's really 5 different regression models, and each person is getting the predictions from one of these 5, depending if they were used in the training data or not, for which of them they were used in the training data. And so I'm getting the predictions, and what I'm doing with them is the same. I'm just averaging all of these predictions, and taking the difference. And you can see here that the ATE that I'm getting, the estimate with using the machine learning plugin, is very close to the true ATE. Even though I didn't know what the correct specification of this was. I didn't know exactly what kind of shape this had. The machine learning model just figured it out. Whereas linear regression, it doesn't figure it out. It can't, right? So the ATE is biased downwards. And I can repeat this for many, many different resamples of the data. And I'm going to see that, in fact, this is not unique to this one particular data set. We have actually a pretty substantial bias when we're using linear regression because the model is misspecified. Whereas when we use this machine learning model, it's a lot closer. Now, the question is, when we use linear regression, we know how to compute, we've talked about getting the standard error for the coefficients, and then somehow math happens and we can translate that to a standard error on the plugin estimate of the ATE. What about for machine learning? Well, the problem is that, if you have an arbitrary machine learning model, it's very, very hard, if not impossible, to figuring out what the asymptotic sampling distribution is of the whatever parameters, or maybe there's not parameters, maybe you just go directly for the kind of plugin. It's very complicated. So however, there's a workaround. So there's something called targeted maximum likelihood estimation, and this is in a nutshell for the problem of ATE estimation, or a marginal causal estimand. What you do is you first generate your machine learning prediction. So you predict a value for everyone using typically this kind of cross-fit prediction. So you use different data to predict for each person. Or rather, you make sure that the model that's predicting for a particular person is not trained using their own data. So maybe you have 5 different models, basically. Then you have to get all those predictions. So you're kind of like Y1 and Y0 estimates. And you have to modify them a little bit. And what happens there is actually very simple. It's actually a particular like linear or logistic regression that modifies these things. So you could actually code it by hand. It's not that complicated. But the reason why that is actually what you need to do is that's actually very complicated and requires a lot of math. Feel free to ask me. I have written a book about it. There's also other books that other people have written to describe that, but mine has pretty pictures and theirs don't. So I prefer mine. And then once you have that kind of modified regression function, then you compute the plugin. What does this do? Well, the ATE estimate is going to be a little bit different. But the important thing is that by doing this particular modification, you've actually made it so that this thing now has an asymptotic variance that is given by this formula. And this formula here, this is my tweaked regression model for a equals 1 or a equals 0. And this is something called the propensity score, which we also typically don't know, so we have to estimate it. But what this means is that, okay, I put my regression model here, my plugin, and then I estimate this thing using another model, and then I just take the empirical variance of this whole thing, and that gives me a confidence interval, or a standard error, an estimated standard error. You can divide by root n or whatever to get the finite sample standard error, and I can build a confidence interval. Now you may be thinking, holy shit, that's a lot. So first you're telling me about cross-fitting, and within the cross-fitting, I have to do the model selection and make sure that I didn't fuck that up. And like I said, all of this gets so easier once you've just done it a couple times, but you don't really even have to worry about it. I'm happy to help you. Like if you have a project and you want to do this kind of stuff manually, or talk to biostats students, it really is like a commodity. But you can also just not, right? So there's this TMLE library. You can just load TM library and just say it, and this is what you do. TMLE data y, a, and x. So this is what you basically say. This is my outcome variable. This is my treatment variable, and these are my covariates. And within this, there's extra arguments that you can specify what ML models to use. There's a lot of other like things that you can do. You can see the docs and things like that. But my point is that you don't have to do all this stuff manually. I've just showed you a little bit about what goes on under the hood. And this is what you get out. Boom. This is your ATE estimate. This is your estimated variance, your p-value, your confidence interval. Exactly the same kind of thing that you would get from the linear regression plugin, except now you have a non-parametric regression plugin estimate for your treatment effect. You can also, of course, get risk ratio or odds ratio. This is for ATE. That's why it says additive effect. You can also output all of the predicted outcomes, the counterfactual outcomes, all that other stuff. Now, zooming out a little bit, TMLE is actually a generic recipe for any estimand. So almost any estimand, that most common estimands, I should say. Anything that's like an expectation or a variance, you can do a TMLE for it. And so any part of that you needs like a function to be estimated, just throw all the machine learning stuff at it. And then TMLE will wrap that all up and let you get a confidence interval. Another benefit of TMLE, we'll talk a little bit more about this next time, I think, but it's actually efficient. So out of any possible estimator that you could cook up, TMLE has within any reasonable estimator, there's some mathematical regularity conditions we're not going to get into, but TMLE has the smallest possible sampling variance among those estimators. So you're going to get typically smaller confidence intervals with TMLE than you would with linear regression or when you would with an unadjusted estimator. So not only are you getting rid of the bias because you're modeling the conditional means better, and therefore, for example, you don't have the unmeasured confounding of like this nonlinearity that you weren't adjusting for with linear regression. You're just going to find that. So you're getting rid of bias, but you're also getting rid of variance by explaining away more of the variability in the outcome with a more accurate prediction model. And in fact, this, like I said, mathematically proven. You can't really do better. You cannot do better than this. That doesn't mean it's always going to do best in a given sample, but asymptotically, it's a good bet. Lastly, it's doubly robust. So we haven't talked too much about this, but here, let's say you do a very bad job at estimating your regression model for your outcome, if you still do a good job, like let's say you just did use linear regression here, if you still do a good job estimating this thing called the propensity score, we'll talk a little bit more about that next week, then you will still get an unbiased estimate, which is pretty cool. If you're just doing a standard plugin, if you do a bad job with the outcome regression, you did a bad job and you're done, right? So here you kind of get two chances, which is nice. Some other methods have this property as well. Now, what TMLE does not do, just to remind you, you don't have identification for free. So it lets you estimate. Once you have this conditional, this average over a conditional expectation function, right? Once you have this equality, then you can go from here to here. This is what TMLE lets you do, the best you can possibly do. Now, you still have to assume that you've measured all the confounders. So there's still a gap there. And you have to think, but at least now that's a gap that you can think carefully about using domain knowledge. And you don't need to be worried about, am I doing everything that I could have done to do this estimation, the statistics thing? The statistics is pretty much done and taken care of. And now your only problem is really worrying about the science. So that's wonderful. So just know that you still have to think scientifically. You just don't have to worry so much about the stats, okay? So that's nonparametric regression. A quick summary here. Nonparametric regression, very similar to what we're used to with linear logistic regression. It's just you're searching a larger or a different set of functions. The goal is still the same. Next point is that interpretability, kind of tricky. You can do it, but honestly, I think it's a good thing that it's tricky because it stops you from turning your brain off and just reading these coefficients off the table and saying that they mean something. And next, prediction. It's very easy to do prediction. Just as easy as anything else. Generally, you'll do a lot better with these methods than with linear logistic regression. You just have to be careful, and you do model selection using cross-validation or holdout test set to estimate the final error, and you're good to go. Lastly, you can use TMLE to leverage these arbitrary machine learning models to get plugin estimators of causal effects, which eliminates model misspecification bias typically, and two, often reduces the variance of your estimate as well. And for this, there's also internal cross-validation that is happening to do the model selection typically. And you can dig into that package to figure out all of the different little things that you can do. There's also courses on this, by the way. You can look up courses that Mark Vanderland teaches, and they'll be way over your head in most places, but at least the labs, you sit on those and you'll learn how to use these packages pretty effectively. So that's it. Next time we'll come back and wrap up the course. See you then.